All right, so we're continuing with our results from yesterday about reviewing the classification of finitely generated abelian groups. So if you just go to the end of the last video, I'm picking up basically exactly where I left off there. So actually, let me turn the page and just to say what we have. So we're trying to sketch out the proof of this theorem. What we have is there's a pair of free abelian groups. One is G2, and it's contained inside G1. And this Smith normal form, this big theorem from matrix theory, tells us that you can get bases that have a certain form, right? So the point is you pick a basis of G2, which I'm calling here E1 through En. You pick a basis of G1, F1 through Fm, and after applying the Smith normal form, you can arrange this very simple form. So if you take E1, so remember G2 is contained in G1, so if you take E1 and you regard it as an element of G1, it has an expansion in terms of the F's, right? And it's saying that this expansion is B1, F1. If you take E2, it's B2, F2, and all the way up to En being Bn, Fn. So it says that this inclusion has like kind of the simplest, you can pick bases so that this inclusion has the kind of simplest possible form. Okay, so what does that mean practically, what does that mean practically speaking? Well, it means that when you take remember that we have the A, so recall that the group A, we have, let's put it this way, G1, there's a surjection from G1 onto A called phi, and kernel of phi was exactly G2. Okay, so these two things together imply, so let's pause and make a general statement now about group theory. These two statements together imply that if you take a G1 and you take the quotient by G2, that's isomorphic to A. So fact. If you have these two things, you get that G1 quotient out by G2 is isomorphic to A, right? So where this is the quotient group, right? So if you have one abelian group sitting inside another, as we know, it's possible to take the quotient, right? The set of equivalence classes where the equivalence relation is, X is equivalent to Y if the difference between X and Y is in G2, right? So that's the general definition of a quotient of one abelian group by another. And the point is that if I have G1 mapping to A whose kernel is G2, that's just the same as saying that G1 mod G2 is A, right? And the reason is that, how do I make this identification? The identification is through the map phi, right? So the point is that if X and Y, so if X and Y are in G1, then phi of X equals phi of Y. Okay, that's the same as saying that phi of X minus Y equals 0, right? And that's the same as saying that X minus Y is in G2, right? And that's the same as saying that X is equivalent to Y under the G2 equivalence relation, right? So if you kind of unpack all this, what you see is that if I take the group that I get by taking the elements of G1 and identifying any two elements when they differ by an element of G2, that's just the same. That's exactly the same as A, right? The map phi takes such an equivalence class and identifies it with an element of A. Okay, so what does it mean then that A is isomorphic to G1 mod G2? If I further know that this is my presentation of G1 inside G2. So now, what is this G1 mod G2? So now we can compute. So the kind of next step is to say we can compute G1 mod G2 via the basis. Maybe the better way to say it is no, that's fine. I'll say the basis F1 through Fm. So what does it mean? Okay, let's go over to the next page. By the way, I'm going to scan all these notes tomorrow and post them. So if you want to follow along with the scan, that should be possible fairly soon as well. Okay, so what does this mean? So G2, so remember that G2 is precisely the subgroup generated by E1 through En. Let's make sure I have my N's and M's straight. Yep, E1 through En, which is precisely B1, F1, B2, F2, Bn, Fn. Right? So it's the subgroup generated by these. Okay? So if we so to be even more concrete about it, so let's get really concrete. So via the basis, so that's G2 inside G1. Now, if I take G1 mod G2, okay, so this is going to be, maybe before saying that, maybe I'll say something else. So also, or whatever, G1 now is isomorphic to Z cross Z cross Z cross Z M times, right, in such a way that the basis element Fi is corresponding to 0, 0, 1. This is the ith spot, right? So in other words, to give a basis of G1, which is this F1 through Fm, is actually to write an isomorphism with G1 and the kind of simple direct product of Z's, right? Because in fact, the ith basis element goes to just 1 in the ith position, right? So that's our basic free mod. That's our basic fact about bases of free modules. So once that's true, then we can identify G2 with the subgroup, which is spanned by B1 in the first position, B2 in the second position, up through Bn in the, B1 in the first position and all zeros, B2 in the second position and all zeros, up through Bn and all zeros, right? So if we put that together, so G2 is spanned by, generated by. I could say spanned. I mean, it's more of a linear algebra word, but it means the same thing in this context. Anyway, B1, 0, 0, 0, B2, 0, 0, Bn, 0. So Bn is generated or spanned by these elements. So what do you do if you take a bunch of Z's, product of these, and you quotient out by a B1, B2 up through Bn? Well, you get exactly what you think, namely Z mod B1 times Z mod B2 up through Z mod Bn, right? So G1 mod G2 becomes, I'll make sure I'm focused on that, Z mod B1Z cross Z mod B2Z cross up to Z mod Bnz. Now, N and M are not necessarily the same number. M could be bigger than M. And so what's left in the other positions? Well, the subgroup doesn't touch those. So I'm just left with Z's there. So cross Z, cross Z, cross Z, and there are M minus N of those. Okay, so if we flip back to page 1, we'll see that that's the first statement of our theorem. We have an isomorphism between our group, and just to be clear, G1 mod G2 is isomorphic to A, right? So we have an isomorphism from our group A. Let me just maybe say that this is A. So this A is now isomorphic to this product of cyclic groups cross free groups there, and the numbers appearing in these finite cyclic groups, B1 divides B2. That was a consequence of the Smith normal form. So the Smith normal form really implies the classification. It's actually the same theorem in some sense. Okay, so that's the main part of the theorem. That's the existence. And there's another piece of this, which is that this decomposition is actually unique. All right, so maybe I'll talk for a minute about the uniqueness part of things. So, okay, so so maybe the first thing to say is that Yeah, so maybe the very first thing to say about that is that it's not too hard to see that the free part, that if you have two different groups, then the free parts are unique. So yeah. So Goodman's book does this in kind of a nice way. So let me take you through a few aspects of Goodman's proof. So that's existence. Let's now talk next about uniqueness, and then we'll draw out a few more consequences, and then we'll stop. So, so uniqueness says that if we have two such decompositions, if so I'll just rewrite it. Yeah, if A is fixed, if A is isomorphic to F cross Z mod B1 Z mod Bn Z, and at the same time A is isomorphic to F1 cross Z mod A1 Z mod ALZ. Okay, and these aren't just any numbers, these are B1 divides B2 divides Bn, and this is A1 divides A2 divides AL, right? So suppose you have two decompositions like that. These F and F1 are free groups, and then these are finite cyclic groups where the numbers all divide one another in this prescribed way. Then F and F1 are the same, right? So they're free groups with the same rank, they're isomorphic, and the numbers are the same. AI equals BI for all I, including the fact that N is L. So there's so the number of pieces of the decomposition is the same, and the individual numbers that occur are the same. So it's the strongest possible uniqueness theorem. There's really, truly only one way to write down such decomposition. Okay. Yeah. So there's kind of a nice way of doing this, which involves an important notion, which is discussing the torsion inside an abelian group. Now that's worth reviewing in its own right. So I'm going to do that, and then I'm going to explain how that notion kind of proves this uniqueness result. So so this is maybe step. So that was existence, and that took how many steps? 4 steps. So step 5, which is the first step in proving uniqueness, we're going to talk a little bit about torsion. So it's a nice definition. So what's the definition of torsion in an abelian group? So the definition is let A be an abelian group. So the torsion subgroup A tor is precisely the elements of A in A, such that A has finite order. So A has finite order. In the group. Okay. So this is A in A such that N times A is 0 for some N in Z. Okay, so I'm writing the group additively now. So I can add A to itself a bunch of times, i.e. multiply it by a natural number N. Okay, integral number, natural number, either way, and get 0. Okay, and this is a subgroup of A. So this is a subgroup of A. So okay, it's easy to check that it's a subgroup, right? What do you have to check? That if you add 2 torsion elements, you get another torsion element. Well, it's not hard to imagine that that's true, right? Because if one of them is when you multiply it by n, it dies, and the other one, when you multiply it by m, it dies. Multiply the sum by nm or something, right? And the whole sum will die, right? So it's very easy to see that this is closed under addition and negatives and contains 0. That's clear, right? So okay, so it's easy to check that it's a subgroup of A. Okay, so in the case where we have our presentation, so if A is isomorphic to F cross Z mod B1 cross Z mod BR, right? In this case, A tor is simply equal to the finite, all the finite parts. Oh, sorry, I should say B1Z. I should be consistent. People do just say Z mod B1 without writing the Z on the bottom, by the way, but whatever. I'll be consistent as I can be here. Okay, A torsion is just this part, right? Why is that? Because anything, right, if you think about, this is a product of groups, so you have something in the free part, and then a bunch of stuff in all these, in the B1 through BRs. Okay, these are all finite cyclic groups. They're finite groups. So any finite group, all the elements of that finite group have finite order. The basic fact from group theory that we proved back in the day. Finite abelian, even for non-abelian groups, that would be true, right? That you take the cyclic subgroup generated by your element, and it's a finite set, so it's an element of finite. So it's a finite element of finite order. On the other hand, F is a free abelian group. It's a bunch of copies of just Z. It's a cyclic group of infinite order. So any element in F does not have finite order. And so if I'm in the product and I take an element of F cross some element here, if I keep adding it to itself, if the part in F was non-zero, I'll never get 0, right? Because this is just like Z or a bunch of copies of Z. So you can add elements to this as many times as you like, and if you started with a non-zero element, you'll end up with non-zero after all the additions you want to make, right? You multiply by n, you'll never cancel out that part of F. So that's an easy little exercise if you haven't done that. And so the point is that F, when you take a tor, you need the component of F to be 0. So when I say this, I mean I'm in the product and I'm just 0 in the F part and then anything in the Z mod B1 through Z mod BR part. Okay? And furthermore, I have another important thing, which is that A mod A tor is isomorphic to F. Right? So now if I take this quotient group, right, if I take the group where I identify elements if they differ by an element of A tor, the only thing I'll be left over with is F. And again, if you stare at this product of groups construction for a minute, it's kind of obvious, right? Because what does it mean to take an element of this product and then just identify any two whose difference is in A tor? The difference being in A tor means that precisely the first components are equal. So if I make that identification, then I'm just identifying with the first component, which is F. Okay, so again, I haven't said why that's true with the group structure or what have you, but that's not hard to see, and you can look that up in the Goodman's book, or you can just think it through. So A mod A tor is isomorphic to F. So this tells us that F can be recovered out of A. If I just know the group structure of A, I can recover this F, right? I can actually recover that free abelian group from A. I take the torsion part of A and I quotient it out, and then I get F. Right? So this immediately gives us, so let me take the corollary, that if I have two different presentations, right? So if A is isomorphic to F cross a bunch of cyclics, regardless of the actually any conditions on the multiplicities, which is further isomorphic to F1 cross a bunch of cyclics, a bunch of finite cyclic groups, A, L, Z, the numbers don't matter there, then F is isomorphic to F1. And the proof is both of them are A mod A tor, right? So the proof is both are A mod A tor, right? So the proof is actually one line immediate from this discussion of torsion, right? So if I look in the first presentation, the torsion subgroup is this finite cyclic part. When I quotient by it, I get that F. If I look in the second presentation, the torsion subgroup is this business, and I get F. When I quotient, I get that F1. So since A mod A tor is a well-defined thing, right, it doesn't depend on the particular presentation, right? When I take A mod A tor, I just take the group A, I look at the torsion subgroup, and then I take that quotient. That doesn't care if I presented it this way or if I presented it this way. That's just, it only depends on A. So I've written A mod A tor in two ways. In one way, through this presentation, I got F, and through this presentation, I got F1, and so I would deduce then that F and F1 are isomorphic. So that tells us exactly the first part of uniqueness, which is that the free part, the free rank of the group, is the same, no matter which presentation you get. F and F1 are actually the same group. Okay, so that's, not only is their rank the same, but I can actually make a canonical isomorphism between them by identifying both of them with A mod A tor. Okay. I won't say what I mean by canonical isomorphism, but it's a very nice, suffice to say, it's a very nice proof. Okay, and so then the rest of the part is to deal with the finite part. So then the next thing we need that A tor, since A tor now has two presentations, first is this product of finite cyclic groups, and second is this product of finite cyclic groups, then what we need to show is that if you have a group which is all torsion, which is just a product of finite cyclic groups, it has only one presentation. Okay, so you can assume so for the rest of the uniqueness proof. So to get the rest of uniqueness, you can suppose that A is A Tor is a finite abelian group. Right, so the heart of the uniqueness proof, like the core of the work after this freeness business that we just did, is to prove that when you have a finite abelian group, if you have two different decompositions of it into products of cyclic groups where the numbers divide, each one divides the rest, then those decompositions are equal. Okay, so that's the thing to do. Okay, so the way to do this is to use what's called the period of a finite abelian group. So let me make a definition. The period. So let A be a finite abelian group. The period. So the period of A. Often pair of A. So it's the integer that annihilates. It's the how to say, the least natural number that annihilates all of A. So is the minimum of elements n in n such that n times all of A is 0. Okay. So let's stare at that definition for a minute. So in other words, you have a finite abelian group. Every element in this finite abelian group is annihilated by some integer. If I take all the elements of my finite abelian group, I look at their integers that annihilate them, and I multiply all those integers together, right? I'll get some huge integer that annihilates every single element of the group, right? So because it's actually literally a finite group, finite set, I can find a single integer number that annihilates everything. But now the point is that the set of numbers that annihilate everything is itself a subgroup of Z. And so that subgroup has a generator, which is this minimum. So to rewrite this is a generator. So the subgroup generated by the period of A in Z, this is the subgroup of Z, which consists of elements which annihilate A. Of Z consisting of elements, integers, yeah, I'll just say integers, that's better than elements probably, that annihilate A. Okay? So in other words, you if I take the collection of integers in Z that annihilate A, that's a non-trivial subgroup of Z. It's not just 0. It's clearly a subgroup because if I have one integer that annihilates A and another one, and I add them, then the sum will annihilate A. You can see that easily. And so, in fact, it's a subgroup. It's generated by a single element. What element is that? By our general theory of subgroups of the integers, that element is this minimal natural number that we just wrote down on the other page. So that's what the period of A is. And now we have a little claim, which is that if A is Z mod B1 cross Z mod BR, with B1 divides B2 divides BR, right? So suppose you have a little situation like this, which is exactly what we do have, then the period of A is BR. Okay. So again, I'm not going to write out a detailed proof of this in my notebook, but I'll just say in words what's going on. So what's going on with this is that, the point is that this divisibility thing is the crucial point. So whenever I have a cyclic group, it's clear that the number on the bottom will annihilate every element of the cyclic group, right? If I have Z mod n, then n is exactly the period, right? I think that's easy to see. And now the point is that since since B1, since all these lower b's divide into BR, BR is a multiple of them, so BR will also annihilate all of these other groups, right? So the point is BR annihilates Z mod BR, but it also annihilates Z mod BR minus 1, precisely because BR minus 1 divides into BR. And so you can show that it annihilates each one, and furthermore, because there is a copy of Z mod BR in there, it's the smallest possible thing that could annihilate 0, 0, 0, 0, 0, and then 1 in there. So you can kind of check, you can kind of think through what it can annihilate, and you can kind of check that BR will annihilate. BR will be precisely the annihilator, so it'll be precisely the period. Okay, so yeah, so what is this? So what we're going to do is we're going to do a little induction on, well, not quite on the period, but on the, as Goodman puts it, on the length, so the number of primes occurring in a prime factorization of A. So to get uniqueness, we induct on, I'll follow Goodman's notation here, length A, which is the number of primes in the prime factorization. A prime factorization, that's not right. The prime factorization of, sorry, he calls it little a, but let me be completely clear that the number is period of A. So the length of the period of A, so this is number of primes in the prime factorization of this number period of A, including multiplicity. So what do I mean by that? If the period of A can be factored as, make sure I show that on the screen, P1 to the N1, PL to the NL, then the length of the period of A is N1 plus N2 plus NL. Right? So it's the number of primes in counting multiplicity. Right? In other words, when I take a prime number and I have it to some power, that increases the length. Okay. So the claim is that we're gonna do an induction. We're gonna do a uniqueness theorem. We're gonna do an induction on this length of A. So what's the base case? So the base case is if the length of A is 1, right? So base case here, the length of the period of A is 1. What does that mean? That means precisely that the period of A is a prime number. So if the period of A is a prime number, that means that you have a factorization and this BR is prime, and all of the numbers lower in the factorization divide into BR. If BR is prime, that means that there are no other numbers. So this is the same as saying that A is just Z mod PZ. And then it's clear that this is unique, right? There's not multiple ways of writing. I mean, Z mod PZ is not a product of groups. It cannot be written as a product of groups in any way, right? This right? So this clearly implies that the factorization is unique. So clearly this clearly implies uniqueness. Immediately, I'll just say uniqueness, exclamation point. Right? It clearly implies that such a factorization of the group, right? In other words, I have a factorization of a group like this, and now I'm saying, is it unique? Yes, there's only one number there, and it's prime. So there's clearly no other way to write this thing. Okay, so that's the first. So that's the base case. Yeah, that's right. Okay, so well, okay. The words I said there were a little bit glib, because it might not be true that there's only one prime. It might be true that all of the numbers are equal. So, okay, instead of being lazy, I'll be not lazy. I know that you guys did this before in class, but probably you want at least some more overview. So, okay, so that was kind of glib. I just said uniqueness, exclamation point. So, maybe I'll actually take it back. So this implies that A is equal to Z mod P cross Z mod P cross Z mod P. Okay, and the point is that it cannot be a product of six, right? So in other words, what it means is that all of the BIs are equal to one another because they all divide each other, and the top one is a prime number, right? So can A also be a product of Z mod P's by a different number of them? So let's say this is R times, and so if A is also Z mod P cross Z mod P S times, then that implies that S is R, and the reason is just look at the size of A. The size of A. Right? If R and S are different numbers, you would have that the same group has two different sizes as a set, which is impossible. Okay, so if the period is prime, then whenever you have a factorization like this, because they have to divide, all the numbers have to divide each other, all the numbers that appear are prime, and then that implies that the length of the factorization is the same, because the length of the factorization determines literally the size of the set. And since the set is the same size, this is the same set, you need that R would have to be equal to S. Okay, so that was my, instead of just saying uniqueness exclamation point, I'll just I'll give you a little bit of the argument here. Okay. All right. So yeah. All right. So how do we then go about proving this? Yeah. So we're gonna try to kind of sketch out what the rest of this inductive argument looks like. So yeah. So let's see. What's the best kind of way to do it here? Right. So the idea is that we're doing a kind of induction on the length, right? And so the claim is that we know we have two different decompositions. We know that that this group has a certain period, and that this period must be the top number in either, both, all of these decompositions of it into cyclic groups, right? And so now the point is, yeah. So maybe the way to, I mean, there's a couple different ways that you might go about doing this. I'll try to again. We're at 32 minutes here, so again, these things are all ending up longer than I thought. So I'll just try to sketch out what's done in Goodman's way. So yeah. So maybe the way to do it is to take any prime in the decomposition and kind of take your group and quotient out by that prime. So that's basically what Goodman does. So let me give you the final skinny here. Okay. So for the inductive argument, so let period of A P1N1 PRNR in general, right? So suppose we're doing our inductive argument, and we've done it for all primes of all numbers whose lengths are less than a certain number, and now we come across a new number whose length is this n1 plus nr. Okay. So what we want to do is we want to look at any prime in this decomposition, and we want to take a quotient out by that prime. Okay. So let's look at we look at A modulo P J A for any PJ in what did I call it? P1 through PR. Okay, so for any one of those primes, so what does it mean? Again, so PJ times A is a subgroup, right? So PJ times A, just to review, is a set of literally anything that can be written as PJ times something. So it's A and A such that A is P sub j times A prime. Right, and again, by our kind of general knowledge of abelian groups, we know that this is a subgroup, and we know that you can take the quotient by it, right? And so now the point is that what you can do is you can take this quotient and you can use the decomposition of A to figure out kind of exactly what it is. So if A is isomorphic to Z mod B1Z plus Z mod BRZ, right, then, okay, so A mod P1A is isomorphic to, okay, now, so it's this mod P1 times this. So maybe before I say that, let me just say, what is Z mod BZ mod P times Z mod BZ? So what is that actually? Well, actually, there's two distinct possibilities. It's either Z mod PJ or it's 0. So what are the two choices? It's 0 if PJ doesn't divide B, and it's Z mod PJZ if PJ divides into B, right? Because PJ is prime, right? The point is PJ is prime. So either it's a factor of B, or if it's not a factor of B, then it's relatively prime to B, right? Its GCD with B is 1, and so it's a unit in Z mod B. So this thing you know right away because you know when things are units. So if this is a unit, when I multiplying by it is it hits every element, right? It has an inverse, and so in fact this group PJ times Z mod BZ is the whole thing, and so the quotient has to be 0. And now with the other option, if PJ divides into B, B is PJ times something, and so now I'm just back to my cyclic group quotient by cyclic group business, right? So in fact, what I can say is that A mod P, so A mod PJA is actually isomorphic to, well, it's a product of Z mod PJs, and I just look at where the PJs divide the BIs. So it's the product of Z mod PJZ, and the product is indexed over PJ divides BI. So remember, the period of A, which is BR, has some prime factorization, and then I look at all those primes, all these B1s divide into BR, and so these are the only possible primes that can be dividing into these numbers, right? This is the only list, and so I look at all of those ones, and I quotient out by them, right? And so the point is that okay, so this is Z mod, so this is Z mod PJZ to the K to write it. Okay, I'll do it that way to write it explicitly. Yeah. Okay. So the point is that yeah. So then what you want to say is that yeah. So this K is the, yeah, exactly. K is the number of BI such that PJ divides BI, right? And so the point is this K is determined completely. It determines and is determined completely by A, right? If A mod PJA is some group, and its size is PJ to the K, so K only depends. It doesn't depend on the particular decomposition of A into this product. It only depends on A itself. That's kind of a theme. To reiterate, we did the same thing before when we talked about torsion. We gave a description of some numbers, and they only depended, the point is that they only depended on A. Why am I emphasizing that? Because remember, what we're trying to prove is that something is unique. So that if I have two different decompositions, I would get the same numbers out, right? So in order to get something like that, I have to look as much as I can at things that only depend on A itself. Okay? So So the point is that the number of BI's, just that PJ divides BI, is exactly this K. So if we pick, so now pick P, so let's just have it, let's just call it P1, so let P1 be divided into B1. All right, so P1 is one of these primes that is factoring the period. Suppose that it divides the very first number B1, then this implies that P1 divides BI for all I, right? Because each B divides them. And this implies that K for this P1 is actually R. Okay? So in fact, you can recover the number of factors R by taking a certain prime and letting and looking at the exponent K that you get when you take that prime. Okay? So using this kind of argument, you can show that if I have another decomposition, so let me now note that, of course, what we really are considering is, suppose I have two decompositions, Z mod AL, C. You can use this to deduce that R is L, right? Because note that the way that I got this R, this number R, which is the number of elements in this decomposition, I cooked it up out of completely just an invariant of the group itself, just taking A and looking at primes and looking at the kind of biggest number I could get. So I can use this to deduce that R is equal to S. R is equal to L, excuse me. So this implies that R is equal to L since K is equal L for such primes also. Okay, so again, I'm being just a little bit vague in the argument. I encourage you to look in Goodman's book or notes from Aaron's lectures for more details, but you can use this kind of argument. Just remember, K only depends on the size of A mod PA. So this K totally only depends on A, and once I know that, then using the two decompositions, I can force R and L, so the number of elements here and the number of elements in this decomposition, to be the same. Okay, so yeah, and then furthermore, I can kind of push this argument a little further, because once you know that there's some prime that divides, the argument will also imply that there's some prime that divides both B1 and A1. And so then the point is that P, if for that prime, P times A is also a finite abelian group of a smaller length. So finally we note that also P times A is a finite abelian group of a smaller length. And so that induction group of smaller length. So I'll zoom out on this in a second. Like I said, I'll post these notes tomorrow. Right? And this allows you to do induction, right? So the point is that once you force the number of elements in the number of pieces of the product to be the same on each side, then you turn around, you take one of these primes and you say, this is a finite abelian group, its length, its period, so smaller length. When I say it's of smaller length, I mean its period has smaller length. So let me be more precise, whose period has. Yeah, so just to really not so any confusion. So the period of P times A is the period of A divided by P. You can check that easily. And so this is a finite abelian group whose period has smaller length than that of A. And so then this, by induction, the numbers for this thing are determined, and then you can use that and this kind of argument to show that the numbers for A are determined. And so this allows you to imply induction. So this allows the induction to move forward. So again, like I said, the point of this review is not to provide all the details, but just to sketch out the kind of ideas that you need. So you need torsion, you need periods, and then you need a little argument about taking your group and quotienting out by different primes to force the to get this induction hypothesis to go. Okay, so that's 45 minutes. That's actually another almost class. So I'm going to stop now. I'm going to photocopy and post these tomorrow, and then we're going to proceed with, I guess, a third smaller class which will be a review of the different forms of the theorem. I'll probably try to post that tomorrow. And then finally, for like Friday's actual class, we'll get to some new stuff. Okay, looking forward to talking to you guys tomorrow on Piazza and stuff.